Hello, everyone, and welcome back. Today, we are going to be talking about the slope of a tangent from first principles. Just a reminder, we haven't done derivatives yet in this. However, all of these questions can also be solved using derivatives and other methods as well. But today, I'm going to be focusing on how to find slope of a tangent from first principles specifically. So before we get into that though, I want to talk about what do we mean by the slope of a tangent? Well, how do we find the slope of a line? If I asked you that question today, or even in grade 9 or 8 or 7 maybe, you'd probably tell me, well, slope is equal to rise over run. Or you might say slope is equal to delta y over delta x, right? You'd probably tell me one of those things. Or maybe you'd tell me that it's y2 minus y1 over x2 minus x1, right? Any of those things is correct. And that is how we identify the slope of our line. Now, the thing with a line is very consistent, right? A line always has the same slope no matter what part of the line we're looking at. It does not matter. A curve is another story, though. With a curve, the slope changes, right? Sometimes we might have a very steep slope, other times a not a steep slope. Also, a curve might change direction, so we might have a positive slope sometimes and a negative slope other times. And so, basically, a slope of a tangent specifically, a slope of a tangent line is referring to a slope of a curve. The straight, like the tangent line is the straight line that represents the slope of the curve at that point the best we can. So, for example, at this turning point here, it looks like the slope is zero, right? We're getting a horizontal line there that best represents what the graph is doing at that very point. But if I choose a point over here, then I think this line would be more appropriate. This is a better tangent line. What if I choose over here? Well, then it's going to be a negative tangent line. And so a slope has multiple different tangent lines, right? There's ways for us to find the general equation of the slope of the tangent line, but once we plug in the x value, that will tell us what is the slope at that specific point as well. And we're going to do both those things today. So let's move on to what is the formula from first principles. Well, here it is. The slope is equal to the limit as h approaches 0, f of x plus h minus f of x over h. So we have a question, and it asks, determine the slope of the tangent to the line f of x equals x squared at the point p 3, 9. Okay, so first thing we need to do is we need to first find the general slope, right? What is the slope in general of the equation? And then we need to figure out, well, at p equals, at the point 3, 9, where x is equal to 3, what is the slope at that specific point? And then we're going to measure it up to what we know f of x equals x squared to look like. And we're going to say that makes sense or that does not make sense. Of course, just graphing it and looking at what we think the graph looks like it might be is not enough. However, it's a great way to check to make sure that we most likely got it correct and that the answer we gave didn't make any sense. So, for example, if we were to solve it using first principles and then we graphed it and realized that the answer we got was a negative answer, but we were supposed to get a positive answer, it was supposed to be a positive slope according to what we got, then there's clearly a problem there. There's a discrepancy there. So I think that drawing the graph and drawing an approximate tangent line is really good for checking to see if you're correct, but it's not going to be accurate enough to be able to just rely on that as a method. We need to do it algebraically in order to get it to be accurate. So let's do it. So the slope is equal to limit as h approaches to 0 of, let's see, f of x plus h becomes x plus h squared, because what does this function do? This function takes whatever the input is, which is whatever's in the brackets, and it squares it, right? So in this case of f of x plus h is our input, we're squaring that input, right? Then we have minus f of x, so minus x squared over h. Now I'm going to expand and simplify. So my next step, I'm going to use the distributive property to expand this and get x squared plus 2xh plus h squared minus x squared over h. And then I notice I have x squared minus x squared, so those cancel. And I also notice I can factor out an h from here, and then I can cancel these h's. And then at this point, we no longer have h in the denominator. So we can just plug in the 0 from limit as h approaches 0, because we will no longer get something that's undefined. And we will just get 2x plus h, which h is 0, which is just 2x. So 2x is the answer. In order to find the slope of the tangent at any point on f of x equals x squared, the answer is 2x. So at this specific point, it would be 2 times 3, which is 6. So the slope in this specific case, right, is going to be 2 times 3, which is 6. Now, does that make any sense to us? Let's draw a graph really quick and figure it out. So we have a graph that kind of looks like this, and at 0.39, let's say that's up here, we have a pretty steep slope. And so I would say that sounds about right, and it also is in the correct direction too, right? It's a positive number we got, and looks like we have quite a positive steep slope. And so that makes good sense to me that that is the accurate number. Besides that, I do know it's the accurate number, but just as a method to check, because we won't always get things like x squared or something that simple. Now, you might be saying, isn't there an easier way to do this? And yes, there is. Just by finding the derivative using the power rule, that is an easier way. And we'll talk about power rule and all the other derivative rules and how to use them very shortly. However, in this video specifically, we're just going to solve using first principles. Okay. Sometimes on a test, you may be asked to use this specific method, so it's important to know it, even though, yes, there are faster, better methods out there if we are being honest with ourselves. Of course, there are. Okay, let's try this example 2. This one's going to use the same general method, and so is example 3 for that matter, but there is a little bit of a different thing we need to do to actually solve it and get it down to the very final step in this example, because we have a fraction here, and also in the next example because we have a square root. So over here, the x squared and the minus x squared, they canceled out really nicely, and then we just had to factor out an h, and then we were rolling, right? It might not be that easy in these next 2 examples, but I'm going to show an example of each for that purpose. So in example 2, it says determine the slope of the tangent to this line. So just a reminder that m is equal to the limit as h approaches 0, f of x plus h minus f of x over h, which in this case is equal to what? Well, what does this function do? It says to multiply the input by 3 and add 6, and then take all of that over the input, right? So everywhere I see an x, I'm going to replace it with x plus h. So instead of 3x plus 6, I'm going to write 3x plus h plus 6. And then instead of x at the bottom, I'm going to replace it with, you guessed it, x plus h. And then I'm going to subtract f of x, so I'm just going to subtract 3x plus 6 over x. And all of this is over h. Now I need to, in some way, simplify this subtraction that we have on the top of our fraction. And how do we subtract fractions, or add fractions for that matter? We need to make sure that the denominators are the same. And going back to like grade 3 math, how can we get the denominators to be the same? We multiply by 1 to make the denominators the same. So I'm going to do that. I'm going to multiply the first fraction by x over x times x over x. And then the second fraction I'm going to multiply by x plus h over x plus h, like that. And let's ignore the third question for now. I'm just going to continue on because we don't have a lot of space. So as you'll notice now, all of my denominators are about to be the same, and that's good. That's exactly what I would like. Okay, so now let's continue. Here we have limit as h approaches to 0, 3x plus 3h plus 6 times x over x times x plus h. And then over here we have subtract, let's see, if we use our distributive property, right, our FOIL method, we're going to get 3x squared plus 3xh plus 6x, let's see, plus 6h. Yeah, it's the last one I was missing, plus 6h over x times x plus h. And that's all over h. Now I'm going to simplify this first one a little bit more. Limit as h approaches 0, 3x squared plus 3xh plus 6x, and then subtract 3x squared minus 3xh minus 6x minus 6h all over x times x plus h all over h. Now I'm going to simplify. So I'm going to say, well, here we have 3x and 3x, or sorry, 3x squared and minus 3x squared, so those cancel. We have plus 3xh minus 3xh, so those cancel. We have plus 6x minus 6x, so those cancel. So most things did end up canceling, it just took us a bit longer to get there. So now we have limit as h approaches 0 of minus 6h over x plus h, and then divided by h. Instead of writing over h, this time I'm going to write divided by h. Now what I'm going to do is I'm going to say, well, if we were dividing by h, that's the same as multiplying by 1 over h. So let's do that. And now we can cancel out these h's, and we end up with the limit as h approaches 0 of minus 6 over x to the x plus h. And now we do have the ability to plug in that 0, right? Because we're no longer going to have 0 as our denominator. We are now going to have as our denominator negative 6 over x plus 0, which is going to be negative 6 over x squared. And so there we go. There is our answer. Now they told us to do it at x equals 2 specifically. So my last step is just to plug in 2 and say that m therefore is equal to negative 6 over 2 squared, which is negative 6 over 4 equals negative 3 over 2. And so negative 3 over 2 is the answer. So there we go. All right, so I know that one was a long one, but let's recap what we do if we have fractions as our function here that we are trying to find using first principles. Well, what we need to do then is we need to make sure that the denominators of the fractions that we are subtracting are the same. Then we expand and simplify those fractions. Then at the very end, we change the over h in the original equation to divided by h, which is really times 1 over h, and we use that to cancel it out with the h on in the numerator in the very end. So it's going to be that same method for every single one of this type of question, which is the good thing. The bad thing is this is a lot of steps, right? It's a lot of unnecessary steps that we don't really have to do, as there are better methods, but sometimes you'll be asked to find the slope of the tangent or find the derivative using first principles. Okay, so I'm going to erase that, and we're going to be doing example 3 next. And then that'll be it for today. We'll do something else in another time. Okay, example 3. Find the equation of the tangent line to y equals root x at point P93. Okay, so for this one, same way we start, just a reminder, m is equal to the limit as h approaches 0, f of x plus h, subtract f of x over h. Okay, now we're going to sub in our equation, right? So we're going to treat y the same as f of x, okay? So the input, it's saying we're going to square root everything, right? So we're going to take this input, x plus h, and square root it. We're going to square root our x because that is what the function does. Now the question is, in this case, how do we simplify further? in this situation, right? I mean, I could plug in 0 now, but I would get something undefined. What we need to do is we need to multiply by the conjugate, okay? We need to multiply by the conjugate. So the conjugate is x plus h plus root x. And basically what this does, why I'm choosing this specific value to add, right? Or sorry, to multiply by, and of course I have to, make sure I'm just multiplying by 1, right? I have to put the same thing, numerator and denominator. But the reason I choose this is because this creates a difference of squares, right? Whenever we have a difference of squares, if we recall from grade 10, whenever we have a difference of squares, we can multiply the first two and multiply the last two, and then the outer and inner in the FOIL are just going to cancel each other out every single time. And so therefore we get rid of some of these roots. So I'll show you what I mean here. And by the way, conjugate is just where we write the same root values, but we just change the subtraction sign to an addition sign or vice versa. So notice I wrote the same values, I just switched what sign we were using in order to get the conjugate. So let's do that in practice. If I was to multiply these through, I would get x plus h, right? Because root x plus h times root x plus h is just x plus h. Then next I would get for outer, I would get plus root x plus h. And then for inner, I would get minus root x plus h. And then last, I would get minus x squared. Or sorry, just minus x rather, not minus x squared. So notice here in this scenario that our outer and our inner just cancel. So you don't even have to write those. You can just not bother to write those if you don't want to. I also notice that minus x plus x, they cancel as well. So now all I'm left with is h over h times root x plus h plus root x, like that. And the limit as h approaches to 0. So now I'm just going to cancel out my h's, and we're going to get that it's going to be a limit as h approaches 0 of 1 over all this stuff. And if I was to right now plug in h equals 0, guess what I wouldn't get? I would not get 0 in my denominator, so I am welcome to do that now. Whereas in the previous step, before we canceled that last h out, we would have gotten 0 in our denominator, as it would have been 0 times some other number in our denominator, which would have been 0. So therefore, we have root x plus root x, which is 1 over 2 root x. And there's our answer. Now it asked for a specific point. It was 9. Okay, 9, 3. So that means the x value is 9. So our slope is 1 over 2 times root 9, which is 1 over 2 times 3, because we're assuming that because it's a function, we're only doing the positive root in this case, equals 1 over 6. And so 1/6 is our final answer there. So as you noticed, it was the same thing basically 3 times. One of them, though, we just had to expand and simplify. The second, we actually had to do some subtraction and just remember some things from back in elementary school and apply those same tools and techniques to our variables in order to find the answer. And then in this last one, we had to apply the conjugate, and we had to recognize that the correct thing to multiply the numerator by, and therefore the denominator by as well, since we can only multiply by 1, was the conjugate and what the conjugate was. So that's a very key point here that I want to make sure we get across, right? Because, of course, we can always just multiply by 1, regardless of how we write the 1, but which way of writing 1 out of the infinitely many ways will actually get us to where we need to go? That is the real question, right? And that depends on what our goal is, right? Is our goal to get rid of some square roots, right? Then maybe a conjugate. Is our goal to add or subtract fractions? Well, then maybe we need to do it according to what is going to make the denominators the same and the easiest way possible. But yeah, that is basically it for today. I will see everybody next time. Next time, we will be talking about rates of change. And this is not the same rates of change we did in grade 12 advanced functions. This is a different rates of change where we will be applying calculus methods that we've learned to our rate of change as well. So good work today, everyone, and we will see you next day for rates of change. Bye, everyone.